If you're watching this on a smaller screen, consider expanding to full view. The details matter here, not for spectacle, but because the structures we will examine exist at scales that challenge comprehension even when given full attention. And if this exploration resonates, consider subscribing, not for algorithmic favor, but because the questions we are tracing will continue and they will deepen. Now let us begin. Somewhere in the universe, approximately 13 billion light-years from Earth, exists an object that should not be possible according to the timeline we have constructed for cosmic history. It is a supermassive black hole, an entity whose mass exceeds that of millions or even billions of suns, and it exists at a point in time when the universe itself was less than 1 billion years old. The James Webb Space Telescope, humanity's most advanced infrared observatory, has measured this object with unprecedented precision. The measurements are not ambiguous. They are exact within the limits of instrumental error. The black hole's mass has been determined. Its accretion rate has been estimated. Its electromagnetic signature has been analyzed across multiple wavelengths. And the conclusion drawn from this data is simple, yet profoundly destabilizing to existing models. This black hole has grown far too massive, far too quickly, given the amount of time available since the beginning of the universe. To understand why this matters, we must first understand what a black hole is, not as metaphor or abstraction, but as a physical consequence of general relativity operating under extreme conditions. A black hole forms when matter is compressed into a region of space so small and so dense that the curvature of space-time becomes infinite at a central point called the singularity. Surrounding this singularity is an event horizon, a boundary beyond which the escape velocity exceeds the speed of light. Nothing that crosses this boundary can return, not because it is pulled with infinite force, but because all future paths through space-time lead inexorably inward. The event horizon is not a physical surface. It is a mathematical boundary, a point of no return defined by the geometry of space-time itself. Black holes form when massive stars exhaust their nuclear fuel and collapse under their own gravity. In stars with sufficient mass, typically more than 20 times that of the Sun, the core collapse is so rapid and so complete that not even the pressure of degenerate neutrons can halt it. The core contracts past the neutron star threshold and continues collapsing until it forms a black hole. This process is relatively well understood. The resulting black hole, formed from a single stellar collapse, typically has a mass between 5 and 50 times that of the Sun. These are called stellar mass black holes. They are common in galaxies throughout the universe. Their formation mechanisms are well documented. Their properties are predictable. They pose no theoretical difficulties. Supermassive black holes are different. They exist at the centers of most large galaxies, including our own Milky Way, and their masses range from hundreds of thousands to tens of billions of solar masses. The supermassive black hole at the center of the Milky Way, known as Sagittarius A*, has a mass of approximately 4 million suns. The black hole at the center of the galaxy M87, famously imaged by the Event Horizon Telescope, has a mass of approximately 6.5 billion suns. These objects are not simply larger versions of stellar mass black holes. They are fundamentally different in scale and, crucially, in their formation history. A stellar mass black hole forms in seconds during the collapse of a massive star. A supermassive black hole, by contrast, must somehow accumulate its immense mass over cosmic time scales, accreting matter from its surroundings, merging with other black holes, and growing incrementally over millions or billions of years. The difficulty arises when we observe supermassive black holes in the very early universe. The universe is approximately 13.8 billion years old. The cosmic microwave background, the afterglow of the Big Bang, shows us the universe as it was approximately 380,000 years after its beginning, at the moment when it became transparent to light. Before this time, the universe was a hot, dense plasma, opaque to electromagnetic radiation. After this time, neutral atoms formed, light could travel freely, and the first structures began to condense from the primordial gas. The formation of the first stars, known as population 3 stars, is estimated to have occurred between 100 million and 200 million years after the Big Bang. These stars were massive, short-lived, and composed almost entirely of hydrogen and helium, the only elements present in significant quantities at that time. When these stars died, they would have produced the first stellar mass black holes. From a starting point, supermassive black holes must somehow form. The traditional model assumes that stellar mass black holes, once formed, begin to accrete matter from their surroundings. Gas, dust, and occasionally entire stars fall toward the black hole, spiraling inward in an accretion disk, releasing tremendous amounts of energy in the form of radiation before crossing the event horizon. As the black hole consumes matter, it grows. Over millions of years, it can increase its mass significantly. Additionally, black holes can merge with one another, combining their masses and producing even larger black holes. Over the course of cosmic history, through repeated cycles of accretion and merging, stellar mass black holes could, in principle, grow into supermassive black holes. The problem is time. Specifically, the problem is the rate at which a black hole can grow through accretion. This rate is not arbitrary. It is limited by a fundamental physical constraint known as the Eddington limit. When matter falls toward a black hole, it does not simply vanish silently into the event horizon. As it spirals inward, friction within the accretion disk heats the material to extraordinary temperatures, causing it to emit intense radiation. This radiation exerts an outward pressure on the surrounding material, counteracting the inward pull of gravity. If the accretion rate becomes too high, the radiation pressure becomes so strong that it halts further infall, effectively capping the rate at which the black hole can grow. The Eddington limit defines this maximum accretion rate as a function of the black hole's mass. For a black hole of a given mass, there is a maximum luminosity it can emit while still allowing matter to fall inward, and this luminosity corresponds to a maximum accretion rate. The Eddington limit can be expressed mathematically, but its essence is simple. A black hole can, at most, approximately double its mass every 50 million years if it accretes continuously at the Eddington limit. This is an upper bound, not a typical rate. Real black holes do not accrete continuously at maximum efficiency. Accretion is episodic, irregular, and often interrupted by feedback mechanisms where the energy released by the black hole expels surrounding gas, temporarily halting further infall. In practice, black holes grow more slowly than the Eddington limit would allow. Now consider the timeline. If the first stellar mass black holes formed approximately 200 million years after the Big Bang, and if they began accreting immediately at the Eddington limit without interruption, how massive could they become by the time the universe was 1 billion years old? The available time is 800 million years. If a black hole doubles its mass every 50 million years, it can undergo 16 doubling periods in 800 million years. Starting from a stellar mass black hole of, say, 30 solar masses, 16 doublings would yield a black hole with a mass of approximately 2 million solar masses. This is a respectable mass, certainly enough to qualify as a massive black hole, but it is not a supermassive black hole by the standards of the objects observed in the early universe. And yet, observations of quasars in the early universe have repeatedly revealed supermassive black holes with masses exceeding 1 billion solar masses at times when the universe was less than 1 billion years old. These objects are not rare anomalies. They have been found in significant numbers. Their existence is confirmed through multiple independent methods, including spectroscopic measurements of their accretion disks, gravitational lensing studies, and, most recently, direct measurements from the James Webb Space Telescope. The black hole that prompted this discussion is one such object, measured with extraordinary precision, and its mass far exceeds what the standard accretion model can explain. This discrepancy is not a minor detail. It is a fundamental challenge to our understanding of structure formation in the early universe. If supermassive black holes cannot grow from stellar mass seeds within the available time, then one of several possibilities must be true. Either the seeds themselves were much more massive than stellar mass black holes, or the accretion rate was somehow much higher than the Eddington limit, or black holes formed through an entirely different mechanism that does not require gradual growth at all. Each of these possibilities has profound implications, and each requires us to reconsider aspects of cosmology, astrophysics, and general relativity that have been considered well established for decades. Let's first consider the possibility of more massive seeds. If the first black holes were not formed from the collapse of individual stars, but instead from the direct collapse of massive gas clouds, they could begin with much larger initial masses. A gas cloud collapsing directly into a black hole, without first forming a star, could produce a black hole with a mass of tens of thousands or even hundreds of thousands of solar masses. This is known as a direct collapse black hole, and it is one of the leading theoretical models for explaining supermassive black holes in the early universe. However, direct collapse requires very specific conditions. The gas cloud must be massive, rotating slowly, and, crucially, it must not fragment into smaller clumps that would form stars instead of a single black hole. Fragmentation is suppressed if the gas remains hot, which in turn requires that the gas does not cool efficiently through radiation. In the early universe, cooling is primarily achieved through molecular hydrogen, which forms naturally in primordial gas. If molecular hydrogen is present, the gas cools fragments and forms stars. If molecular hydrogen is absent or destroyed, the gas remains hot and direct collapse becomes possible. What could prevent molecular hydrogen from forming or destroy it once formed? The answer is radiation. Specifically, ultraviolet radiation in a narrow energy range, known as Lyman-Werner radiation, can dissociate molecular hydrogen without ionizing the surrounding gas. If a region of the early universe is bathed in Lyman-Werner radiation from nearby stars or galaxies, molecular hydrogen cannot form, and the conditions for direct collapse are met. This is a plausible scenario, but it is also highly contingent. It requires the right sources of radiation, the right gas distribution, and the right timing, all occurring in close proximity. It is not clear whether these conditions were common in the early universe or whether they were rare. Simulations of early structure formation produce mixed results, with some models predicting that direct collapse black holes form frequently and others suggesting they are uncommon. Even if direct collapse black holes did form, they still face the same Eddington-limited growth problem, albeit starting from a higher initial mass. A black hole that begins with a mass of 100,000 solar masses still needs to grow by a factor of 10,000 to reach 10 billion solar masses. At the Eddington limit, doubling every 50 million years, this requires approximately 13 doublings, or 650 million years. If the black hole forms at 200 million years after the Big Bang, it could reach the required mass by 850 million years after the Big Bang, which is within the observational window. However, this calculation assumes continuous accretion at the maximum rate, with no interruptions, no feedback, and perfect efficiency. Real astrophysical systems are never this ideal. Accretion is messy, turbulent, and subject to numerous instabilities and interruptions. The likelihood that a black hole could sustain maximum accretion for 650 million years continuously is extremely low. This brings us to the second possibility, super Eddington accretion. If black holes can somehow accrete matter at rates exceeding the Eddington limit, they could grow much faster than the Standard Model allows. Super Eddington accretion is not forbidden by physics, but it requires special circumstances. The radiation pressure that limits accretion is most effective when the radiation can escape freely in all directions. If the accretion flow is geometrically thick, or if the radiation is trapped within the flow due to high optical depth, the outward pressure is reduced and matter can fall inward at higher rates. There are theoretical models of super Eddington accretion, often called slim disks or thick disks, in which the accretion rate can exceed the Eddington limit by factors of several or even tens. If such accretion flows were common in the early universe, black holes could have grown much more rapidly. But why would super Eddington accretion be more common in the early universe than in the present day? One possibility is that the early universe had higher gas densities and more abundant fuel for black hole growth. Another possibility is that the dynamics of early galaxies, which were smaller, more chaotic, and more gas-rich than present-day galaxies, facilitated more efficient funneling of gas into black holes. These are plausible ideas, but they are difficult to test observationally. Super-Eddington accretion produces distinctive signatures in the spectrum of the emitted radiation, and careful analysis of quasar spectra from the early universe could, in principle, reveal whether such accretion was occurring. The James Webb Space Telescope is uniquely suited to this task, as its infrared sensitivity allows it to observe the heavily redshifted light from the most distant quasars with unprecedented detail. This is where the recent measurement becomes critical. The black hole observed by the James Webb Space Telescope is not merely massive. Its properties have been measured with sufficient precision to constrain its growth history. The spectrum of the emitted light reveals the velocity of gas in the accretion disk, which in turn allows the mass of the black hole to be calculated using well-established principles of orbital dynamics. The luminosity of the object constrains the accretion rate, and the ratio of luminosity to mass indicates whether the black hole is accreting near the Eddington limit or significantly above or below it. The measurements indicate that the black hole is accreting at or slightly above the Eddington limit, which is consistent with super-Eddington accretion, but not extreme super-Eddington accretion. Even allowing for moderately enhanced accretion rates, the time required to grow this black hole from a stellar mass seed is longer than the age of the universe at the time the light was emitted. This leaves the third possibility, that supermassive black holes formed through a mechanism that does not involve gradual growth at all. What if supermassive black holes did not grow from smaller seeds, but instead formed directly as supermassive objects? This idea, once considered speculative, has gained increasing attention in recent years. One version of this hypothesis involves the collapse of supermassive stars, hypothetical objects with masses of thousands or tens of thousands of solar masses, which could have formed in the very early universe under conditions that no longer exist. Supermassive stars are unstable and short-lived, and they would collapse directly into supermassive black holes without going through the intermediate stages of stellar evolution. Another version involves primordial black holes, hypothetical objects that formed in the first moments after the Big Bang, due to density fluctuations in the early universe. If primordial black holes exist, and if they formed with masses in the supermassive range, they could serve as the seeds for the supermassive black holes we observe today. Both of these ideas are intriguing, but both face significant challenges. Supermassive stars are difficult to form because massive gas clouds tend to fragment into smaller clumps before they can collapse into a single object. Primordial black holes, if they exist, would have observable consequences for the structure of the universe, and current observations place stringent limits on their abundance and mass distribution. Neither idea has been definitively confirmed or ruled out, and both remain active areas of theoretical research. The measurement from the James Webb Space Telescope does not resolve this mystery. Instead, it sharpens the problem, making it more precise and more difficult to explain. The black hole is too massive, too early, and its properties are too well constrained to dismiss as observational error or theoretical uncertainty. It exists, it is real, and it demands an explanation that our current models do not provide. To appreciate the full weight of this problem, we must step back and consider the broader context of cosmic structure formation. The universe began in a state of near-perfect homogeneity. The cosmic microwave background reveals tiny fluctuations in temperature and density, on the order of 1 part in 100,000. But these fluctuations are the seeds of all structure in the universe. Over time, regions of slightly higher density attracted more matter through gravitational attraction, growing denser and more massive, while regions of lower density became voids. This process, known as gravitational instability, is the fundamental mechanism by which galaxies, stars, and black holes form. Gravitational instability proceeds at a rate determined by the density of matter and the strength of gravity. In the early universe, the matter density was higher, and structures formed more rapidly than they do today. However, the process is still gradual. Small fluctuations grow into larger fluctuations, which collapse into dark matter halos, within which gas cools and condenses to form stars and galaxies. The timeline for this process is constrained by the cosmological parameters we have measured with high precision: the Hubble constant, the density of matter, the density of dark energy, and the amplitude of primordial fluctuations. These parameters, together with the equations of general relativity and fluid dynamics, determine the rate at which structure forms. When we run simulations of cosmic structure formation using these parameters, we can predict the abundance and properties of galaxies, dark matter halos, and black holes at different points in cosmic history. These simulations are extraordinarily detailed, incorporating the physics of dark matter, gas dynamics, star formation, supernova feedback, and black hole accretion. They are run on some of the most powerful supercomputers in the world, and they produce synthetic universes that can be compared directly to observations. In general, these simulations do a remarkably good job of reproducing the observed properties of the present-day universe. They predict the distribution of galaxies, the clustering of matter on large scales, and the abundance of galaxy clusters, all in agreement with observations. However, when we examine the predictions of these simulations for the early universe, discrepancies begin to emerge. The simulations predict that massive galaxies and supermassive black holes should be rare at early times, forming only gradually as smaller structures merge and grow. Observations, particularly from the James Webb Space Telescope, reveal that massive galaxies and supermassive black holes are more common in the early universe than the simulations predict. This is not a small discrepancy. In some cases, the observed abundance of massive structures exceeds the predictions by factors of several or even 10. This suggests that something is missing from the simulations, some physical process or initial condition that has not been properly accounted for. One possibility is that the initial fluctuations in the density of the early universe were not distributed as simply as we have assumed. The standard model assumes that the fluctuations follow a Gaussian distribution, characterized by a power spectrum that is nearly scale invariant. This assumption is well motivated by inflationary cosmology, the leading theory for the origin of these fluctuations, and it is consistent with observations of the cosmic microwave background. However, there is room for small deviations from this simple picture. If the initial fluctuations had slightly higher amplitude on small scales, or if there were rare, high-amplitude peaks in the density field, these could serve as sites for the rapid formation of massive structures. This is known as non-Gaussian initial conditions, and it is a topic of active research in cosmology. Another possibility is that the physics of black hole formation in the early universe was fundamentally different from what we observe today. The first stars, formed from primordial gas with no heavy elements, may have been much more massive than typical stars today, and they may have been more likely to collapse directly into black holes rather than exploding as supernovae. The environments in which these stars formed were also different, denser, hotter, and more turbulent. It is plausible that these conditions favored the formation of more massive black hole seeds, or that they enhanced the efficiency of black hole growth through accretion or mergers. Yet another possibility is that dark matter, the dominant form of matter in the universe, plays a more direct role in black hole formation than we have previously considered. Dark matter halos are the scaffolding on which galaxies form, and the properties of these halos determine the rate at which gas can cool and condense to form stars. If dark matter halos in the early universe were more massive or more concentrated than current models predict, this could accelerate the formation of galaxies and black holes. Some theories of dark matter, particularly those involving self-interacting dark matter or warm dark matter, predict differences in the structure of dark matter halos that could have observable consequences for early structure formation. These possibilities are not mutually exclusive, and it is likely that the true explanation involves a combination of factors. What is clear is that our current understanding of the early universe is incomplete. The observations from the James Webb Space Telescope are not simply filling in details of a well-understood picture. They are revealing phenomena that challenge the foundations of that picture. forcing us to reconsider assumptions we have held for decades. The process of measuring a black hole's mass is itself a remarkable achievement, and it is worth understanding how this measurement is made. Black holes do not emit light, so they cannot be observed directly. Instead, we observe the effects of their gravity on surrounding matter. When gas falls toward a black hole, it spirals inward in an accretion disk, a flattened structure held in orbit by the black hole's gravity. As the gas spirals closer to the event horizon, it moves faster, following the laws of orbital mechanics. The velocity of the gas can be measured through the Doppler shift of spectral lines, features in the spectrum of light emitted by the gas that shift to shorter or longer wavelengths, depending on whether the gas is moving toward or away from us. By measuring the Doppler shift at different positions in the accretion disk, we could determine the velocity profile of the gas as a function of distance from the black hole. The relationship between velocity and distance is determined by the mass of the black hole. According to Kepler's laws, the velocity of an object in orbit around a massive body depends on the mass of that body and the distance from the center. For a black hole, the relationship is particularly simple because the black hole itself is a point mass, with no spatial extent other than the event horizon. By measuring the velocity of gas at a known distance from the black hole, we can calculate the black hole's mass. In practice, the measurement is more complex because we must account for the inclination of the accretion disk relative to our line of sight, the turbulence and non-circular motions in the disk, and the effects of general relativity near the event horizon. However, with careful modeling and high-quality spectra, the mass can be determined with an accuracy of 10 to 20%. The James Webb Space Telescope is ideally suited for this task. Its infrared sensitivity allows it to observe objects at high redshifts, where the light from the early universe has been stretched to infrared wavelengths by the expansion of space. Its large primary mirror collects more light than any previous space telescope, allowing it to observe faint, distant objects with high signal-to-noise ratio. And its suite of scientific instruments includes spectrographs capable of measuring spectra with high spectral resolution, resolving the narrow spectral lines needed to measure Doppler shifts accurately. When the James Webb Space Telescope observes a distant quasar, it collects light that has been traveling through space for billions of years, and it analyzes that light to extract information about the black hole at the quasar center. The measurement is not instantaneous. It requires multiple exposures, careful calibration, and detailed modeling. But the result is a precise determination of the black hole's mass at a specific point in cosmic history. The black hole in question was observed as part of a survey targeting the most distant quasars known. Quasars are among the most luminous objects in the universe, powered by supermassive black holes accreting matter at prodigious rates. They are bright enough to be detected across cosmological distances, even when the universe was less than 1 billion years old. The quasar observed by the James Webb Space Telescope was first identified in earlier surveys using ground-based and space-based telescopes, but its properties were not well constrained until the Webb observations. The Webb data revealed not only the mass of the black hole, but also the properties of the surrounding gas, the rate at which the black hole is accreting matter, and the environment in which the black hole resides. All of these measurements are consistent with a black hole that is actively growing through accretion, but the total mass is so large that it cannot be reconciled with the available time since the Big Bang. This is not the first time such a measurement has been made. Over the past 2 decades, numerous supermassive black holes have been discovered in the early universe, and many of them pose similar challenges to theoretical models. However, the James Webb Space Telescope has provided measurements of unprecedented precision, eliminating the possibility that previous observations were affected by systematic errors or misidentifications. The problem is real, and it is not going away. To understand the full implications, we must consider the cosmological context in more detail. The expansion of the universe is described by the Friedmann equations, a set of equations derived from general relativity that relate the rate of expansion to the density and composition of the universe. The universe is expanding, meaning that the distance between galaxies is increasing over time, and the rate of this expansion is determined by the Hubble constant. However, the expansion rate is not constant. It changes over time, depending on the relative contributions of matter, radiation, and dark energy to the total energy density of the universe. In the early universe, radiation was the dominant component, and the expansion rate was very high. As the universe expanded and cooled, matter began to dominate, and the expansion rate slowed. More recently, dark energy has begun to dominate, and the expansion rate is now increasing. The transition from radiation domination to matter domination occurred approximately 50,000 years after the Big Bang, and the transition from matter domination to dark energy domination occurred approximately 4 billion years ago. These transitions have profound effects on the formation of structure because the rate at which gravitational instability operates depends on the expansion rate. During the radiation-dominated era, density fluctuations could not grow because the pressure of the radiation opposed gravitational collapse. During the matter-dominated era, fluctuations began to grow, first slowly and then more rapidly as structures became denser and gravity became stronger. The era of matter domination is when most structure formation occurred, and it is the era during which the first stars, galaxies, and black holes formed. The timeline for structure formation is therefore intimately tied to the cosmological history of the universe, and any observation that appears to contradict this timeline poses a challenge to our understanding of cosmology itself. The observed black hole exists at a redshift of approximately 10, meaning that the light we observe was emitted when the universe was approximately 500 million years old. At this time, the universe had been matter-dominated for approximately 450 million years, and the first stars and galaxies had been forming for approximately 300 million years. This is a substantial amount of time by human standards, but it is a very short time in the context of cosmic evolution. The fact that a billion solar mass black hole could form within this time frame is the essence of the problem. Let us now consider the process of black hole growth in more quantitative detail. The Eddington limit, as previously mentioned, is the maximum luminosity a black hole can emit while still accreting matter at a steady rate. The Eddington luminosity is proportional to the black hole's mass, and it can be expressed as L_red equals approximately 1.3 times 10 to the 38th times m over m_sun, where L_red is the Eddington luminosity in watts, m is the mass of the black hole, and m_sun is the mass of the sun. This luminosity corresponds to a maximum accretion rate, which can be derived from the relationship between accretion rate and luminosity. If we assume that the accretion process converts a fraction epsilon of the rest mass energy of the accreted matter into radiation, then the accretion rate is given by m_squared equals L over epsilon c squared, where m_squared is the accretion rate, L is the luminosity, epsilon is the radiative efficiency, and c is the speed of light. For a typical accretion disk around a black hole, epsilon is approximately 0.1, meaning that 10% of the rest mass energy is converted into radiation. Using these relationships, we can calculate the maximum accretion rate corresponding to the Eddington luminosity. The result is L_red equals approximately 2.2 times 10 to the negative 8 times m over m_sun solar masses per year. This means that a black hole with a mass of 1 solar mass can accrete at most 2.2 times 10 to the negative 8 solar masses per year, or approximately 2 times 10 to the 21 kilograms per year. For a black hole with a mass of 1 million solar masses, the maximum accretion rate is approximately 0.02 solar masses per year. For a black hole with a mass of 1 billion solar masses, the maximum accretion rate is approximately 20 solar masses per year. Now, if a black hole accretes continuously at the Eddington rate, its mass grows exponentially with time. The growth equation is dm over dt equals approximately 2.2 times 10 to the negative 8 times m, which has the solution m of t equals m_0 times e to the power of t over t_red, where m_0 is the initial mass, t is the time, and t_red is the Eddington time scale, approximately equal to 4.5 times 10 to the 7th years, or 45 million years. This time scale represents the E-folding time for the black hole's mass, meaning that the mass increases by a factor of E, approximately 2.7, every 45 million years. Equivalently, the mass doubles approximately every 31 million years. If we start with a stellar mass black hole of 10 solar masses and allow it to accrete at the Eddington rate for 800 million years, the time available from the formation of the first stars to the observation of the quasar at redshift 10, we can calculate the final mass. The number of E-folding times is 800 million divided by 45 million, approximately 17.8. The final mass is therefore 10 times e to the power of 17.8, approximately 10 times 5.3 times 10 to the 7th, or 5.3 times 10 to the 8th solar masses, or 530 million solar masses. This is a substantial mass, but it is still less than 1 billion solar masses. To reach 1 billion solar masses, the black hole would need to accrete for approximately 860 million years, or would need to start with a more massive seed. If we instead assume that the black hole began as a direct collapse black hole with an initial mass of 100,000 solar masses, the calculation changes. The number of E-folding times is still 17.8, and the final mass is 100,000 times e to the power of 17.8, approximately 100,000 times 5.3 times 10 to the 7th, or 5.3 times 10 to the 12 solar masses, or 5.3 trillion solar masses. This is far too massive, exceeding the observed mass by several orders of magnitude. Clearly, a direct collapse black hole with an initial mass of 100,000 solar masses cannot accrete at the Eddington rate for the entire duration. Either the accretion rate must be lower, or the accretion must be episodic, or both. The real situation is undoubtedly more complex. Black holes do not accrete continuously at the Eddington rate. Accretion is driven by the supply of gas in the surrounding environment, and this supply is not constant. Gas must be funneled toward the black hole, losing angular momentum through turbulence, magnetic fields, or interactions with other gas. Once gas reaches the accretion disk, it spirals inward on a viscous time scale, which can be much longer than the freefall time. Additionally, the energy released by the accretion process can have feedback effects, heating or expelling the surrounding gas and temporarily halting further accretion. These feedback processes are observed in present-day active galactic nuclei, where powerful jets and winds driven by the black hole can evacuate gas from the central regions of the galaxy. In the early universe, the situation may have been different. The gas density was higher, and the halos in which black holes formed were more compact. This could have facilitated more efficient accretion, reducing the impact of feedback. On the other hand, the first stars and supernovae may have injected energy into the surrounding gas, creating turbulence and preventing efficient accretion. The net effect of these competing processes is uncertain, and it can only be determined through detailed simulations that incorporate all the relevant physics. Recent simulations of black hole growth in the early universe have explored a range of scenarios, varying the initial mass of the black hole seed, the accretion rate, the duty cycle of accretion, and the effects of feedback. These simulations produce a wide range of outcomes, with some black holes growing rapidly to supermassive scales and others stalling at much lower masses. The distribution of black hole masses predicted by these simulations can be compared to observations, providing a test of the underlying assumptions. However, the simulations are highly sensitive to the details of the physical processes included, and different choices of parameters can produce significantly different results. This makes it difficult to draw firm conclusions about the viability of different formation scenarios. The measurement from the James Webb Space Telescope provides a critical data point for these comparisons. The observed black hole has a mass that is near the upper end of what the simulations predict, and it may even exceed the predictions depending on the specific model. This suggests that the simulations may be underestimating the efficiency of black hole growth in the early universe, or that they are missing some important physical process. Alternatively, the observation may be probing a rare extreme object that is not representative of the typical black hole population at that epoch. To distinguish between these possibilities, more observations are needed, both to measure the properties of individual black holes with high precision and to determine the overall abundance and distribution of supermassive black holes in the early universe. The James Webb Space Telescope is conducting several large surveys aimed at addressing these questions. These surveys target quasars, galaxies, and other luminous objects at high redshifts, with the goal of building a statistical sample of black holes and their host galaxies. By analyzing this sample, astronomers can determine the typical mass of supermassive black holes as a function of cosmic time, the rate at which they are accreting matter, and the relationship between black hole mass and the properties of the host galaxy. This information is essential for understanding how black holes and galaxies co-evolve, a topic of fundamental importance in astrophysics. The relationship between black holes and their host galaxies is itself a profound puzzle. In the present-day universe, there is a tight correlation between the mass of a supermassive black hole and the properties of the galaxy in which it resides. Specifically, the black hole mass is approximately proportional to the velocity dispersion of stars in the galaxy's central bulge, a relationship known as the M-sigma relation. This correlation is remarkable because the black hole is tiny compared to the galaxy. The event horizon of a supermassive black hole with a mass of 1 billion solar masses has a radius of approximately 3 billion kilometers, or about 20 times the Earth-Sun distance. The galaxy, by contrast, spans tens of thousands of light years, or approximately 10 to the 18 kilometers. The black hole is more than 10 orders of magnitude smaller than the galaxy, and yet the two are intimately connected. This connection suggests that black holes and galaxies influence each other's growth through feedback processes. When a black hole accretes matter, it releases energy that can heat or expel gas from the galaxy, regulating star formation and preventing the galaxy from growing too massive. Conversely, the galaxy supplies the gas that fuels black hole growth, and the dynamics of the galaxy determine how efficiently gas can be funneled toward the black hole. This mutual feedback is believed to be responsible for the observed correlations between black holes and galaxies, and it is a central component of modern models of galaxy evolution. However, the M-sigma relation and other black hole galaxy correlations are derived from observations of nearby galaxies in the present-day universe. It is not clear whether these correlations hold in the early universe, when galaxies and black holes were just beginning to form. If the early universe had different accretion efficiencies, different feedback strengths, or different initial conditions, the black hole-galaxy relationship may have been different. Observations of high redshift quasars provide an opportunity to test this by measuring both the black hole mass and the properties of the host galaxy. Preliminary results suggest that the relationship between black holes and galaxies may have been different in the early universe, with black holes being more massive relative to their host galaxies than they are today. This could indicate that black holes grew more rapidly than galaxies in the early universe, or that the feedback processes that regulate their growth had not yet established the tight correlations we observe locally. The implications of these findings extend beyond the specific question of black hole growth. They touch on fundamental issues in cosmology, such as the nature of the initial conditions of the universe, the role of dark matter in structure formation, and the processes that govern the transformation of primordial gas into stars and galaxies. If supermassive black holes can form much more rapidly than current models predict, this may indicate that the early universe was more conducive to structure formation than we have assumed, with higher gas densities, more efficient cooling, or stronger gravitational instabilities. Alternatively, it may indicate that black holes can form through mechanisms that do not require gradual growth, such as direct collapse or primordial black hole formation. Each of these possibilities has testable consequences. If direct collapse black holes were common in the early universe, they should be detectable as a population of black holes with a characteristic mass distribution and spatial clustering. If super-Eddington accretion was common, it should produce distinctive spectral signatures that can be observed with sensitive spectrographs. If primordial black holes contribute significantly to the supermassive black hole population, They should leave imprints on the cosmic microwave background, the distribution of large-scale structure, and the gravitational wave background. The James Webb Space Telescope, together with other observatories such as the Atacama Large Millimeter Array, the upcoming Extremely Large Telescope, and the planned gravitational wave observatories, will provide the data needed to test these predictions. One of the most intriguing aspects of the James Webb Space Telescope's measurements is the precision with which they constrain not only the black hole's mass, but also its accretion rate and luminosity. The observed quasar is extremely luminous, emitting light at a rate that approaches or slightly exceeds the Eddington limit. This indicates that the black hole is accreting matter at a high rate, close to the maximum allowed by radiation pressure. The fact that the black hole is accreting so efficiently suggests that the surrounding environment is rich in gas and that the conditions for accretion are favorable. However, it also raises the question of how long the black hole has been accreting at this rate. If the accretion has been sustained for hundreds of millions of years, this would help explain the black hole's large mass. But it would also require that the gas supply has remained abundant for an extended period, which is not typical of present-day galaxies. An alternative possibility is that the black hole has been accreting episodically, with periods of high accretion alternating with periods of low or no accretion. If the observed quasar is currently in a phase of high accretion, but spent much of its history in a low accretion state, the average accretion rate over its lifetime would be much lower than the current rate. This would ease the tension with the Eddington limit, but would also require that the black hole went through multiple cycles of accretion and quiescence, each triggered by the infall of new gas. The mechanisms that could drive such episodic accretion are not well understood, but they may involve mergers between galaxies, which can funnel large amounts of gas toward the central black hole, or instabilities in the surrounding gas disk, which can cause sudden inflows of material. Galaxy mergers are particularly relevant in the early universe, where galaxies were more numerous and more closely spaced than they are today. The rate of galaxy mergers was much higher in the early universe, and these mergers are believed to have played a key role in the growth of both galaxies and black holes. When two galaxies merge, their gas reservoirs are disrupted, and the gas can lose angular momentum and fall toward the center of the merged system. If both galaxies contain supermassive black holes, the black holes will eventually merge as well, combining their masses and producing an even more massive black hole. This process of hierarchical growth through mergers is a central component of the standard model of structure formation, and it is expected to be particularly important in the early universe. However, mergers alone cannot explain the rapid growth of supermassive black holes in the early universe. Even if every galaxy merger funnels a large amount of gas toward the central black hole, the timescale for mergers is comparable to the dynamical timescale of the galaxies, which is tens to hundreds of millions of years. This is not fast enough to explain the existence of billion solar mass black holes within the first billion years of cosmic history. Mergers can contribute to black hole growth, but they must be supplemented by efficient accretion from the surrounding environment. Another factor that may influence black hole growth in the early universe is the spin of the black hole. Black holes are characterized by two fundamental properties: mass and spin. The spin of a black hole is a measure of its angular momentum, and it is quantified by a dimensionless spin parameter that ranges from 0 for a non-rotating black hole to 1 for a maximally rotating black hole. The spin of a black hole affects the structure of the accretion disk and the efficiency of energy extraction from the black hole's rotation. A rapidly rotating black hole can extract energy from the rotation through processes such as the Blandford's-Najek mechanism, in which magnetic fields threading the event horizon tap the black hole's rotational energy and convert it into powerful jets. These jets can carry away a significant fraction of the accretion energy, potentially affecting the growth rate of the black hole. The spin of a black hole evolves over time as it accretes matter and merges with other black holes. Accretion tends to spin the black hole up, particularly if the accreted matter has a consistent angular momentum direction. Mergers can either increase or decrease the spin, depending on the relative orientations and spins of the merging black holes. The spin of the black holes observed in the early universe provides information about their accretion history and merger history, and it can be measured through observations of the accretion disk and the emitted radiation. The James Webb Space Telescope is capable of measuring the properties of accretion disks with sufficient precision to constrain the black hole spin, although this requires high-quality spectra and detail modeling. The environment in which the black hole resides also plays a critical role in its growth. Supermassive black holes are not isolated objects. They are embedded in galaxies, which are themselves embedded in dark matter halos. The properties of the dark matter halo, such as its mass, concentration, and merger history, determine the amount of gas available for accretion and the rate at which gas can be delivered to the black hole. In the early universe, dark matter halos were smaller and less massive than they are today, but they were also more numerous and more actively forming through mergers. The interplay between dark matter halo growth and black hole growth is a key aspect of structure formation, and it is an area of active research. Simulations of structure formation track the evolution of dark matter halos and the baryonic matter within them, including gas, stars, and black holes. These simulations begin with the initial conditions of the universe, as determined by observations of the cosmic microwave background, and evolve forward in time using the equations of gravity, hydrodynamics, and radiative transfer. The simulations include a wide range of physical processes, including the formation and evolution of stars, the feedback from supernovae and active galactic nuclei, the cooling and heating of gas, and the growth of black holes through accretion and mergers. By comparing the predictions of these simulations to observations, astronomers can test their understanding of these processes and identify areas where the models may be incomplete or incorrect. The simulations have been remarkably successful in reproducing many observed properties of the present-day universe, but they struggle to reproduce the abundance and properties of galaxies and black holes in the early universe. This is particularly true for the most massive galaxies and the most massive black holes, which are more common in observations than the simulations predict. This discrepancy is sometimes referred to as the impossibly early galaxy problem or the impossibly massive black hole problem, and it is one of the most pressing challenges in cosmology today. Several explanations for this discrepancy have been proposed, ranging from modifications to the initial conditions of the universe to changes in the physical processes governing star formation and black hole growth. One possibility is that the simulations underestimate the efficiency of gas cooling in the early universe, leading to slower star formation and black hole growth than actually occurred. Another possibility is that the simulations do not properly account for the effects of radiation from the first stars and quasars, which can heat or ionize the surrounding gas and affect its ability to cool and form stars. Yet another possibility is that the simulations are missing entirely new physical processes, such as the formation of direct collapse black holes or the contribution of primordial black holes, which are not included in the standard models. Resolving this discrepancy will require both better observations and better simulations. On the observational side, the James Webb Space Telescope is providing unprecedented data on the early universe, revealing the properties of galaxies and black holes at high redshifts with a level of detail that was not previously possible. On the simulation side, advances in computational power and numerical methods are enabling more realistic and higher-resolution simulations that can capture the complex physics of structure formation. The combination of these two approaches will be essential for understanding the origin and growth of supermassive black holes in the early universe. The question of how supermassive black holes formed so rapidly in the early universe is not just a technical problem for astrophysicists and cosmologists. It is a profound question about the nature of the universe itself. The existence of these objects challenges our understanding of time, gravity, and the fundamental processes that govern the evolution of cosmic structure. If black holes can grow much more rapidly than we thought, this may indicate that the early universe was fundamentally different from the late universe, with different physical conditions and different dominant processes. Alternatively, it may indicate that our understanding of black hole physics is incomplete and that there are mechanisms of black hole growth that we have not yet discovered. One of the most intriguing possibilities is that black holes themselves played a more active role in shaping the early universe than we have previously appreciated. In the present-day universe, supermassive black holes are known to influence their host galaxies through feedback, regulating star formation and preventing the galaxies from growing too massive. In the early universe, when galaxies were smaller and black holes were forming more rapidly, this feedback may have been even more important, shaping the distribution of gas and the formation of stars in ways that we are only beginning to understand. If this is the case, then supermassive black holes are not merely passive products of structure formation. They are active agents that help to determine the structure and evolution of the universe itself. This idea has profound implications for our understanding of cosmic history. It suggests that the universe we observe today is the result not just of the gravitational growth of structure, but of a complex interplay between gravity, gas dynamics, star formation, and black hole growth, with each process influencing the others in ways that are difficult to predict. It suggests that the universe is more dynamic, more interconnected, and more sensitive to initial conditions than we have assumed. And it suggests that small changes in the early universe, such as the formation of a few unusually massive black holes or the presence of a slightly higher gas density in certain regions, could have cascading effects that shape the entire subsequent history of structure formation. These are not idle speculations. They are testable hypotheses, grounded in the data provided by observations like those from the James Webb Space Telescope. By measuring the properties of black holes and galaxies in the early universe, astronomers can trace the history of structure formation and identify the processes that were most important at different times. By comparing these observations to the predictions of simulations, they can test different models of black hole formation and growth, and identify which models are consistent with the data and which are not. This iterative process of observation, modeling, and comparison is the essence of the scientific method, and it is the process by which our understanding of the universe advances. The James Webb Space Telescope's measurement of this particular black hole is just one piece of a much larger puzzle. It is a crucial piece because it provides a precise, quantitative constraint on the mass and growth rate of a black hole in the early universe. But it is not the only piece. There are many other observations from many other telescopes and surveys that are contributing to our understanding of this problem. There are observations of other high-redshift quasars, observations of early galaxies, observations of the cosmic microwave background, observations of gravitational waves, and observations of the large-scale structure of the universe. Each of these observations provides a different perspective on the same underlying question. How did the universe evolve from a nearly uniform state shortly after the Big Bang to the rich, complex structure we observe today? The answer to this question is not yet known, but it is gradually coming into focus. The observations from the James Webb Space Telescope are revealing that the early universe was more active, more dynamic, and more surprising than we had expected. Galaxies formed earlier, stars formed more rapidly, and black holes grew faster than the standard models predicted. This does not mean that the standard models are wrong, but it does mean that they are incomplete. There are physical processes at work in the early universe that we have not fully accounted for, and understanding these processes is one of the most important challenges facing cosmology today. One of the key insights from recent observations is that the early universe was not a simple, uniform place. It was a complex, heterogeneous environment, with regions of high density and low density, regions of active star formation and quiescent regions, regions where black holes were growing rapidly and regions where they were not. This heterogeneity is a natural consequence of the gravitational instability that drives structure formation, but it also makes the universe more difficult to model and predict. In a perfectly uniform universe, structure formation proceeds smoothly and predictably, with small fluctuations growing into larger fluctuations at a rate determined by the cosmological parameters. In a heterogeneous universe, the growth of structure is more complex and more sensitive to local conditions, and different regions can evolve in very different ways. This heterogeneity is particularly important for understanding black hole growth in the early universe. If black holes form and grow in regions of high gas density, where the conditions for accretion are most favorable. Then the abundance and properties of black holes will depend on the distribution of these high-density regions. If such regions are rare, then supermassive black holes will also be rare, and the few that do form will be unusual objects that are not representative of the typical environment. If such regions are common, then supermassive black holes will be more abundant, and they will be a more typical feature of the early universe. The observations from the James Webb Space Telescope suggest that supermassive black holes are more common than the simulations predict, which in turn suggests that the conditions for rapid black hole growth were more widespread in the early universe than we have assumed. Another important insight is that the early universe was a time of rapid change. The transition from a universe dominated by radiation to one dominated by matter, the formation of the first stars, the onset of reionization, the assembly of the first galaxies, and the growth of the first black holes all occurred within the first billion years of cosmic history. This is a very short time compared to the age of the universe, and it represents a period of intense activity and transformation. Understanding the sequence and timing of these events is essential for understanding how the universe evolved from its primordial state to the state we observe today. Reionization, in particular, is a key process that occurred during this period. In the early universe, after the formation of the cosmic microwave background, the gas in the universe was neutral, composed primarily of hydrogen and helium atoms. As the first stars and quasars formed, they began to emit ultraviolet radiation, which ionized the surrounding gas, converting neutral atoms into free electrons and protons. This process of reionization gradually spread throughout the universe, until eventually all the gas was ionized. The timing and duration of reionization are not precisely known, but it is believed to have occurred between approximately 200 million and 1 billion years after the Big Bang. The James Webb Space Telescope is observing galaxies and quasars during this era, providing direct evidence of the sources of ionizing radiation and the progress of reionization. The relationship between reionization and black hole growth is complex. On the one hand, reionization is driven by the ultraviolet radiation from stars and quasars are powered by supermassive black holes. This suggests that black hole growth and reionization are linked, with the same objects contributing to both processes. On the other hand, reionization can affect black hole growth by heating the surrounding gas and making it more difficult for gas to cool and accrete onto black holes. This feedback effect could slow the growth of black holes during the reionization era, potentially explaining why some black holes did not grow as rapidly as others. The interplay between reionization and black hole growth is an area of active research, and it is one of the key questions that the James Webb Space Telescope is designed to address. By observing galaxies and quasars during the reionization era, astronomers can determine the relative contributions of stars and black holes to the ionizing radiation, measure the properties of the ionized regions around these objects, and trace the evolution of the ionization state of the universe over time. This information is essential for understanding the role of black holes in cosmic history and for determining whether they played a significant role in reionizing the universe. The measurement of the black hole's mass and accretion rate also provides information about the efficiency of black hole growth. Efficiency, in this context, refers to the fraction of the available gas that is actually accreted by the black hole, as opposed to being ejected, heated, or otherwise prevented from reaching the event horizon. In present-day galaxies, the efficiency of black hole growth is relatively low, with most of the gas in the galaxy never reaching the black hole. This is due to a combination of factors, including the limited supply of gas in the central regions, the angular momentum of the gas, which prevents it from falling directly inward, and the feedback from the black hole itself, which can expel gas and halt further accretion. In the early universe, the efficiency may have been different. The gas density was higher, the galaxies were more compact, and the feedback mechanisms may not have been as effective. This could have allowed black holes to accrete a larger fraction of the available gas, leading to more rapid growth. However, measuring the efficiency directly is difficult, because it requires knowledge of both the amount of gas accreted by the black hole and the total amount of gas available in the surrounding environment. The James Webb Space Telescope can measure the accretion rate by observing the luminosity of the quasar, but measuring the total gas content of the host galaxy requires observations at longer wavelengths, such as millimeter or submillimeter wavelengths, where the cold gas emits thermal radiation. These observations are typically conducted using facilities like the Atacama Large Millimeter Array, which can map the distribution of molecular gas in distant galaxies with high spatial resolution. By combining observations from the James Webb Space Telescope and the Atacama Large Millimeter Array, astronomers can determine both the accretion rate of the black hole and the gas content of the host galaxy, allowing them to calculate the efficiency of black hole growth. Preliminary results from such studies suggest that the efficiency was indeed higher in the early universe, with black holes accreting a larger fraction of the available gas than they do today. This supports the idea that the conditions in the early universe were more conducive to rapid black hole growth, and it provides a partial explanation for the existence of supermassive black holes at early times. However, even with higher efficiency, the problem of rapid growth remains. A black hole that accretes 10% of the gas in its host galaxy can grow significantly, but it still needs a substantial initial mass and a long period of sustained accretion to reach supermassive scales within the first billion years. This brings us back to the question of the initial mass of the black hole seed and the mechanisms by which such seeds could form in the early universe. The formation of black hole seeds is one of the least understood aspects of black hole astrophysics. In the present-day universe, black holes form primarily through the collapse of massive stars, and the resulting black holes have masses in the range of a few to a few tens of solar masses. These stellar mass black holes can then grow through accretion and mergers, but as we have seen, this growth is limited by the Eddington limit and by the availability of gas. To explain the existence of supermassive black holes in the early universe, we need a mechanism that can produce more massive seeds, or a mechanism that can accelerate the growth of stellar mass seeds beyond what the Eddington limit would normally allow. Several mechanisms have been proposed for producing massive black hole seeds. One is the collapse of supermassive stars, as mentioned earlier. Supermassive stars are hypothetical objects with masses in the range of thousands to tens of thousands of solar masses, which could have formed in the early universe under special conditions. These stars would be unstable and short-lived, collapsing directly into black holes without undergoing a supernova explosion. The resulting black holes would have masses comparable to the mass of the progenitor star, providing a massive seed for further growth. However, the formation of supermassive stars requires very specific conditions, including the absence of heavy elements, which would cause the star to lose mass through radiation-driven winds, and the presence of a large, rapidly collapsing gas cloud, which can overcome the tendency of the gas to fragment into smaller clumps. Another mechanism is the direct collapse of gas clouds into black holes, without forming stars at all. This is the direct collapse black hole scenario, which we have discussed previously. In this scenario, a massive gas cloud collapses under its own gravity, but the collapse is so rapid and so complete that it bypasses the normal stages of star formation and produces a black hole directly. This requires that the gas remain hot during the collapse, which in turn requires that molecular hydrogen, the primary coolant in the early universe, be absent or destroyed. This can be achieved if the gas is exposed to a strong ultraviolet radiation field, which dissociates the molecular hydrogen and prevents it from cooling the gas. The direct collapse black hole scenario is attractive because it naturally produces black holes with masses in the range of tens of thousands to hundreds of thousands of solar masses, which are much larger than stellar mass black holes and which can serve as seeds for supermassive black hole growth. However, the conditions required for direct collapse are stringent, and it is not clear how common these conditions were in the early universe. A third mechanism involves primordial black holes, which are hypothetical black holes that formed in the first moments after the Big Bang, before the formation of stars and galaxies. Primordial black holes could have formed from density fluctuations in the very early universe, if the fluctuations were sufficiently large and dense to overcome the pressure of the surrounding matter and collapse directly into black holes. The mass of a primordial black hole depends on the size of the density fluctuation and the density of the universe at the time of formation, and it can range from microscopic masses to many solar masses. If primordial black holes with masses in a range of thousands to millions of solar masses formed in the early universe, they could serve as seeds for supermassive black hole growth. However, the existence of primordial black holes is highly speculative, and there is currently no direct observational evidence for them. Constraints from observations of the cosmic microwave background, gravitational lensing, and a large-scale structure of the universe place limits on the abundance and mass distribution of primordial black holes, and these limits suggest that they cannot account for all, or even most, of the supermassive black holes observed in the early universe. Each of these mechanisms has strengths and weaknesses, and it is possible that multiple mechanisms contributed to the formation of black hole seeds in the early universe. It is also possible that the dominant mechanism varied from place to place, depending on the local conditions. In regions where the gas density was very high and the radiation field was weak, direct collapse black holes may have formed. In regions where massive stars could form and collapse, stellar mass black holes may have been the dominant seeds. And in regions where primordial black holes were present, they may have contributed to the black hole population. Understanding which mechanisms were most important and under what conditions is a major goal of current research. The James Webb Space Telescope is not only observing individual black holes in the early universe. It is also surveying the population of black holes and galaxies at different cosmic times, providing statistical information about the abundance, mass distribution, and clustering of these objects. By comparing the observed population to the predictions of different formation models, astronomers can determine which models are most consistent with the data. This is a powerful approach because it tests not just individual objects, but the overall statistical properties of the black hole population, which are sensitive to the underlying formation mechanisms and growth processes. One of the key statistical properties of the black hole population is the luminosity function, which describes the number of black holes as a function of their luminosity. The luminosity of a quasar is directly related to the accretion rate of the black hole, so the luminosity function provides information about how rapidly black holes are growing at different times in cosmic history. If black holes are growing primarily through continuous accretion, the luminosity function should be relatively smooth, with a gradual decline at high luminosities. If black holes are growing primarily through episodic accretion or mergers, the luminosity function may be more irregular, with bumps or features corresponding to the times when accretion or mergers are most common. The James Webb Space Telescope is measuring the luminosity function of quasars at high redshifts with unprecedented precision, and the results are revealing features that were not predicted by the standard models. Another key statistical property is the clustering of black holes and galaxies, which describes how these objects are distributed in space. If black holes form preferentially in high-density regions, they should be more strongly clustered than the overall distribution of matter. If black holes form randomly, their clustering should be weaker. By measuring the clustering of quasars and galaxies at high redshifts, astronomers can infer the typical mass of the dark matter halos in which these objects reside, and they can determine whether black holes are forming in the most massive halos or in a broader range of environments. The James Webb Space Telescope is contributing to these clustering measurements by identifying large samples of quasars and galaxies at high redshifts, which can be combined with data from other surveys to map the three-dimensional distribution of these objects. The relationship between black holes and their host galaxies is also being probed in detail by the James Webb Space Telescope. In the present-day universe, supermassive black holes are almost always found at the centers of galaxies, and their masses are correlated with the properties of the galaxy, such as the mass of the stellar bulge and the velocity dispersion of stars. This correlation suggests that black holes and galaxies grow together, with feedback from the black hole regulating star formation in the galaxy, and the galaxy supplying gas for black hole growth. In the early universe, this relationship may have been different. If black holes grew more rapidly than galaxies, the correlation between black hole mass and galaxy mass may have been weaker, or it may have had a different slope. If feedback from black holes was less effective in the early universe, the correlation may have been absent altogether. To test these ideas, astronomers are measuring both the black hole mass and the stellar mass of galaxies at high redshifts. The black hole mass is determined from the properties of the quasar, as we have discussed. The stellar mass is determined from the brightness of the galaxy in different wavelength bands, which provides information about the number and type of stars present. By comparing the black hole mass to the stellar mass for a large sample of galaxies, astronomers can determine whether the black hole-galaxy relationship at high redshifts is similar to or different from the relationship in the present-day universe. Preliminary results suggest that the relationship was indeed different, with black holes being more massive relative to their host galaxies at high redshifts than they are today. This supports the idea that black holes grew more rapidly in the early universe, outpacing the growth of their host galaxies, and that the feedback mechanisms that establish the tight correlations we observe locally had not yet fully developed. The implications of these findings extend far beyond the specific question of black hole growth. They have profound consequences for our understanding of galaxy evolution, star formation, and the overall history of the universe. If black holes played a more dominant role in the early universe, influencing the formation of stars and the distribution of gas in ways that are not captured by current models, then our entire picture of how galaxies form and evolve may need to be revised. This is not a small adjustment. It is a fundamental rethinking of the processes that shape cosmic structure, and it requires us to reconsider the relative importance of different physical mechanisms at different times in cosmic history. One of the most exciting aspects of this research is that it is still in its early stages. The James Webb Space Telescope has only been operating for a short time, and it is already producing results that challenge existing models and raise new questions. As more data are collected, and as the observations become more detailed and more comprehensive, we can expect to see further surprises and further revisions to our understanding of the early universe. This is the nature of scientific progress. Observations drive theory, theory makes predictions, and new observations test those predictions, leading to a continuous refinement of our understanding. The process is iterative and cumulative. Each new observation builds on previous observations, each new theory builds on previous theories, and each new insight deepens our understanding of the universe. The measurement of a single black hole in the early universe may seem like a small step, but it is part of a much larger effort to understand the origin and evolution of cosmic structure. It is a step that adds to our knowledge, that constrains our models, and that points the way toward new questions and new investigations. The black hole measured by the James Webb Space Telescope is not just an object of curiosity. It is a window into a time when the universe was fundamentally different from what it is today, a time when the first structures were forming, when the first stars were lighting up, and when the first black holes were beginning to grow. By studying this black hole and others like it, we are learning about the conditions in the early universe, about the processes that govern structure formation, and about the physical laws that shape the evolution of the cosmos. This knowledge is not merely academic. It is essential for understanding where we came from, how the universe came to be the way it is, and what the future holds. The universe is vast and complex, and our understanding of it is far from complete. But with each new observation, with each new measurement, we move closer to a more complete picture. The James Webb Space Telescope is one of the most powerful tools we have for exploring the universe, and its measurements of black holes in the early universe are among the most important contributions it is making to science. These measurements are challenging our assumptions, forcing us to reconsider our models, and opening up new avenues of research that will occupy astronomers and cosmologists for years to come. The question of how supermassive black holes grew so rapidly in the early universe is not merely a technical problem to be solved by adjusting parameters in a computer simulation. It is a profound mystery that goes to the heart of our understanding of the universe. It forces us to confront the limits of our knowledge, to question our assumptions, and to explore new ideas that may seem radical or counterintuitive. It is a reminder that the universe is full of surprises, and that even the most well-established theories can be challenged by new observations. In the end, the significance of the James Webb Space Telescope's measurement lies not in the specific numbers it has produced, but in the questions it has raised and the pathways it has opened for future exploration. The black hole it has measured is a signpost, pointing toward a deeper understanding of the universe and beckoning us to continue the journey of discovery. The universe does not give up its secrets easily, but with patience, persistence, and the right tools, we can gradually unravel the mysteries that surround us. The process of scientific discovery is slow and painstaking, but it is also cumulative and progressive. Each generation of scientists builds on the work of previous generations, refining and extending our understanding of the natural world. The James Webb Space Telescope represents the culmination of decades of effort by thousands of scientists, engineers, and technicians, all working toward the common goal of exploring the universe and expanding the boundaries of human knowledge. The measurement of a single black hole in the early universe is just one of many discoveries that this remarkable instrument will make, but it is a discovery that exemplifies the power of science to reveal the hidden workings of nature and to challenge our preconceptions about the world around us. As we continue to explore the universe with the James Webb Space Telescope and other observatories, we can expect to encounter more surprises, more challenges, and more opportunities for discovery. The universe is a vast and complex place, and we have only begun to scratch the surface of its mysteries. But with each new observation, with each new measurement, we move closer to a more complete and more accurate understanding of how the universe works, where it came from, and where it is going. The black hole that the James Webb Space Telescope has measured is a reminder that the universe is not static or unchanging. It is a dynamic, evolving system shaped by the interplay of gravity, gas dynamics, radiation, and the fundamental forces of nature. Understanding this system requires not just observations, but also theory, modeling, and a deep engagement with the fundamental principles of physics. It requires us to think carefully about the assumptions we make, the models we build, and the interpretations we draw from the data. It requires us to be open to new ideas, to be willing to revise our theories in light of new evidence, and to maintain a healthy skepticism about our own conclusions. The measurement of this black hole is also a testament to the power of technology to extend the reach of human perception and to enable us to explore realms that would otherwise be inaccessible. The James Webb Space Telescope is a marvel of engineering, a precision instrument capable of detecting the faint light from objects billions of light years away and analyzing that light to extract detailed information about the properties of those objects. It is a tool that allows us to see farther, to see more clearly, and to see things that previous generations of astronomers could only dream of. And it is a tool that is enabling us to answer questions that have puzzled humanity for centuries, questions about the origin of the universe, the nature of time and space, and the place of life in the cosmos. The black hole measured by the James Webb Space Telescope is a single object, but is also a representative of a population of objects that existed in the early universe. By studying this black hole and others like it, we're learning about the conditions that prevailed in the early universe, about the processes that drove the formation of structure, and about the evolution of galaxies and black holes over cosmic time. This knowledge is essential for understanding the history of the universe and for placing our own existence in a broader cosmic context. The existence of supermassive black holes in the early universe also raises questions about the nature of time itself. Time, as we experience it, is a continuous flow, a progression from past to present to future. But in the context of cosmology, time is more complex. The expansion of the universe means that the distance between galaxies is increasing over time, and this expansion affects the rate at which light travels from distant objects to our telescopes. When we observe a distant galaxy or quasar, we are not seeing it as it is now, but as it was in the past, when the light we are observing was emitted. The farther away an object is, the farther back in time we are looking. This means that observations of the early universe are also observations of the distant past. When the James Webb Space Telescope observes a black hole at a redshift of 10, it is observing that black hole as it was approximately 13 billion years ago, when the universe was less than 1 billion years old. The light from that black hole has been traveling through space for 13 billion years, and it has been stretched and redshifted by the expansion of the universe. By the time it reaches the telescope, it has been transformed from ultraviolet or optical light into infrared light, and it carries with it information about the state of the universe at the time it was emitted. This raises a profound question. What is the relationship between the black hole we observe and the black hole as it exists now? The black hole we observe is a snapshot of the black hole's state 13 billion years ago. Since then, the black hole has continued to grow, to accrete matter, and to evolve. It may have merged with other black holes, or it may have been ejected from its host galaxy through gravitational interactions. It may still exist today, or it may have been destroyed in some cataclysmic event. We have no way of knowing, because the light that would tell us about the black hole's current state has not yet reached us, and will not reach us for billions of years. This disconnect between observation and reality is a fundamental feature of astronomy. We can only observe the universe as it was in the past, not as it is now. The farther we look, the deeper into the past we see, and the more disconnected our observations become from the present state of the universe. This is both a limitation and an opportunity. It is a limitation because it means we can never observe the present state of distant objects, and we must always interpret our observations in the context of cosmic history. But it is also an opportunity because it means we can directly observe the history of the universe, tracing the evolution of galaxies, stars, and black holes from the earliest times to the present. The black hole measured by the James Webb Space Telescope is a time capsule, a relic of the early universe that has been preserved in the form of light traveling across cosmic distances. By studying this light, we're not just learning about the black hole itself. We're learning about the universe as it was in the distant past, about the conditions that existed shortly after the Big Bang, and about the processes that set the stage for the formation of everything we see around us today. This perspective brings with it a sense of humility and wonder. We are observers of a universe that is vastly larger and older than ourselves, a universe that existed for billions of years before we came into being and will continue to exist for billions of years after we are gone. Our observations of distant black holes and galaxies are tiny glimpses into this vast expanse of time and space, brief moments of connection between the present and the distant past. Yet these glimpses are profoundly informative, revealing the fundamental processes that govern the universe and the laws of nature that shape its evolution. The measurement of the black hole's mass and accretion rate is also a measurement of the universe's capacity for self-organization. The universe began in a state of near-perfect uniformity, with matter and energy distributed almost evenly throughout space. Over time, gravitational instability transformed this uniform state into a complex, hierarchical structure of galaxies, stars, and black holes. This transformation is driven by gravity, but it is also shaped by a multitude of other processes, including gas dynamics, radiation, magnetic fields, and feedback from stars and black holes. The result is a universe that is rich in structure, with a wide range of objects and phenomena, each with its own unique properties and history. The black hole measured by the James Webb Space Telescope is one manifestation of this capacity for self-organization. It is a highly concentrated mass, formed from the gravitational collapse of matter, and it exerts a powerful influence on its surroundings. It shapes the distribution of gas in its host galaxy, regulates the formation of stars, and contributes to the overall evolution of cosmic structure. It is both a product of the universe's history and an agent that continues to shape that history. Understanding how this black hole came to exist, how it grew so massive in such a short time, and what role it played in the early universe requires us to integrate knowledge from many different fields of physics and astronomy. It requires us to understand gravity, as described by general relativity, and how it drives the collapse of matter and the formation of black holes. It requires us to understand gas dynamics, and how gas cools, condenses, and accretes on a black holes. It requires us to understand radiation and how it is emitted by accreting black holes and how it interacts with the surrounding gas. It requires us to understand cosmology and how the expansion of the universe affects the formation of structure. And it requires us to understand the interplay between all these processes, the feedback loops and nonlinear interactions that make the universe such a complex and dynamic system. The challenge of understanding this black hole is not just a matter of collecting more data or running more simulations, although both of these are essential. It is also a matter of developing new theoretical frameworks, new ways of thinking about the processes that govern the universe. It may require us to revisit assumptions that have been taken for granted for decades, or to explore ideas that have been considered too speculative or unconventional. It may require us to integrate insights from different subfields of physics, bringing together ideas from particle physics, nuclear physics, plasma physics, and fluid dynamics, all in the service of understanding how black holes form and grow in the early universe. This is the nature of frontier science. It is not a matter of filling in the details of a well-understood picture. It is a matter of exploring the unknown, of pushing the boundaries of knowledge into realms where our current understanding is incomplete or uncertain. It is a process that requires creativity, rigor, and a willingness to embrace uncertainty. It is a process that is driven by curiosity, by the desire to understand the universe and our place in it, and by the recognition that the universe is full of mysteries that are waiting to be uncovered. The James Webb Space Telescope's measurement of this black hole is a milestone in this ongoing journey of exploration. It is a measurement that has confirmed what many astronomers suspected but could not prove, that supermassive black holes in the early universe are too massive, too early, and too common to be easily explained by existing models. It is a measurement that has sharpened the problem, making it more precise and more urgent, and that has pointed the way toward new lines of research and new opportunities for discovery. The implications of this measurement will reverberate through the field of astrophysics for years to come. It will inspire new theoretical models, new simulations, and new observational campaigns. It will lead to new collaborations between astronomers, cosmologists, and theoretical physicists as they work together to understand the origin and growth of supermassive black holes. And it will contribute to a broader and deeper understanding of the universe, its history, and its underlying physical laws. In the end, the significance of this measurement cannot be fully appreciated in isolation. It is part of a larger tapestry of observations and discoveries, each contributing to our understanding of the universe. The James Webb Space Telescope is observing not just black holes, but also galaxies, stars, planets, and the cosmic microwave background. It is mapping the distribution of matter and energy in the universe, tracing the history of star formation, and searching for signs of life beyond Earth. Each of these observations is a piece of the puzzle, and together they are revealing a universe that is more complex, more dynamic, and more fascinating than we ever imagined. The black hole that the James Webb Space Telescope has measured is a single piece of this puzzle, but it is a piece that fits in a crucial location, helping to constrain our understanding of the early universe and the processes that shaped it. As we continue to collect more data, to refine our models, and to explore new ideas, we can expect to see this puzzle gradually come together, revealing a picture of the universe that is more complete and more accurate than what we have today. The journey of exploration is far from over. The universe is vast, and there is much we do not yet understand. But with tools like the James Webb Space Telescope, and with the dedication and ingenuity of scientists around the world, we are making progress, step by step, observation by observation, toward a deeper understanding of the cosmos. And in that progress, we find not just knowledge, but also a sense of connection to the universe, a recognition that we are part of something much larger than ourselves, and a profound appreciation for the beauty and complexity of the natural world. The black hole measured by the James Webb Space Telescope is a reminder that the universe is full of wonders, that there are still mysteries to be solved and discoveries to be made, and that the pursuit of knowledge is a noble and worthy endeavor. It is a reminder that science is not just a collection of facts and theories, but a process of exploration and discovery, a way of engaging with the world and seeking to understand it. And it is a reminder that, no matter how much we learn, there will always be more to discover, more questions to ask, and more mysteries to unravel. The measurement stands as a testament to human ingenuity and perseverance, to our ability to build instruments that extend our senses across vast distances and to develop theories that make sense of the observations we collect. It is a testament to the power of the scientific method, to the process of hypothesis, observation, and revision that has driven our understanding of the universe forward for centuries. And it is a testament to the enduring human desire to understand the universe, to know where we came from, and to explore the unknown. As the James Webb Space Telescope continues its mission, observing the universe in unprecedented detail, we can look forward to many more discoveries like this one. Each discovery will bring new insights, new challenges, and new opportunities for understanding. And each discovery will remind us that the universe is a place of endless fascination, a place where the past and the present are intertwined, where the smallest particles and the largest structures are connected by fundamental laws, and where the quest for knowledge is an adventure that spans generations and transcends boundaries. The black hole that should not have grown this fast is not an anomaly to be dismissed or explained away. It is a signpost pointing toward new horizons of understanding and inviting us to continue the journey of exploration. The universe is vast, the mysteries are deep, and the adventure has only just begun.